In this video, I will talk about surface charges and how they how they can create an electric field inside a conductor that allows current to flow. Now, we know in order to have current, what we need is charges flowing. Now, for charges to flow, I know that I need to have some force acting on them so that they can move. Now, for the case that we are dealing with, the force, the kind of force that we're talking about is electric force. And in order to have that, I need to have an electric field. Now, constraining myself to the case to electrostatics, where electric fields are produced only by charges, in order to have an electric field, I need to have charges creating that electric field. So this is my thought process. To have a current, I need to have charges flowing, and in most cases these charges are really electrons. Now, to have electrons flowing, I need to have an electric force acting on them, and that means I need to have an electric field. And to create an electric field, I need to have some charges. Now, I'm gonna go back to my picture with my conductor. And let's say that I want, I have an electron here, and I want my electron to go this way. I want my electrons to flow that way. This means that I will have the direction of the electron current. Okay, with lowercase I, I'm using lowercase I for electron current. Is going to point to the right, and of course the direction of the conventional current is going to be the opposite. This is the conventional current. Now I want electrons to flow to the left, and that means the direction of the electric force will be to the right. I want my electrons to move to the right, and that means the direction of the electric force on the electron will be to the right. Now, because the electric force is Q times E, and Q is a negative number in this case, I'm talking about an electron, the electric field needs to point to the left. This is the direction of E, and this is the direction of the electric force on the electron. Now, I know, okay, I'm gonna go back to my thought process. I said that I arrived at the end, I need to have charges. Now, in the case where I'm dealing with a conductor, I know that I cannot have any excess charges in the interior of the conductor. If you remember, in a conductor, all excess charges will need to be on the surface. You will not find any excess charges inside, in the interior of a conductor, such as a wire. So I need to use, I'm gonna go back now to my conductor. I need to use surface charges in order to create an electric field that points to the right. Now I'm gonna show you how this looks like if I use negative charges. So I know from, if I have an electron here, the electric field will need to point towards that electron. The electric field that this source charge creates points towards the electron. Okay, so this is E from a single negative charge. Now, I know that the overall, the total electric field created here, it needs to point to the left. So, and I am constrained on placing electrons on the surface of this wire. So I'm gonna place one electron here. Let's just do the minus sign without the circle. So I'm gonna place an electron here. This is gonna create an electric field at the location of this electron that points that way. But I want the electric field to point to the left, not upwards and left. So what I'm gonna do, I'm gonna place an electron here. This gives me one contribution to the electric field this way and one that way, so that the total is to the left. Now, I want to point out the reason that I have an electric field created at the center is due to a difference of the surface charge that I have here and here. Here I have nothing. Here I have one electron, and the same thing in here. But you can also think of that I have electrons actually everywhere here on that part of the surface of the wire. Okay, I cannot do this 3D picture where I have electrons everywhere, but this is what I want you to keep in mind when you see me drawing an electron here and here. You have these electrons everywhere on that part of the surface. So what I want to point out is that it's the difference that creates the net electric field here. And I can give you an example. If I place some electrons on this side of the surface of the wire, then these two are going to create an electric field to the left. And these two are going to create an electric field to the right. So if you add them together, you get nothing. That's not very useful. I will not have current flowing in this case. But if I place another one here and another one there, then these electrons on the surface are going to create a stronger electric field to the left than the electric field to the right created by these two. So if you take everything together, you still get an electric field in the interior of your conductor that points to the left. So again, it is the difference of the surface charge distribution that gives you an electric field inside. And this is important. So I'm gonna go back. And instead of saying, say difference, I'm gonna, the gradient of the surface charge distribution, what really gives you the electric field that you need, which at the end is going to drive the current. So going back to my conductor, if as you can imagine, you can think of another case where you have 2 here and 3 here. The fact that you have a gradient of that surface charge distribution will still give you a net electric field to the left. So when I have current flowing inside a wire, in order to have that current flowing on the surface of the wire, there needs to be some surface charges, and it is the gradient of those surface charges what drives the current inside that wire. Now, I also want to point out that using minus signs, using negative surface charges, is not the only way to create an electric field. For example, if you have, okay, here is another wire. If I place some positive charge here and I leave nothing on that part of the surface of the wire, I know that the positive charge is going to create an electric field this way. This one is going to create an electric field that way, away from the two. If you add the two together, you get an electric field that points to the left. Now, for the same reason, if you end up adding some more positive surface charges on the left side and you maintain the difference, okay, so now I have 2 and 2, it is true that these two will create an electric field that points to the right, and these ones are going to create a stronger electric field to the left, so that when you add it together, you continue to have your electric field to the left. And if you have 2 here and 2 there and 3 here and 3 there, you can continue to have your electric field to the left, which leads me to the same conclusion. It's the gradient of the surface charge density, the one that allows you to have an electric field inside the conductor. So when we work with circuits, we will need to be thinking that when we have a current, means electrons flowing, an electric force, an electric field charges, we need to have surface charges only because we're dealing with conductors, and in particular we will need to have a gradient of those surface charges being distributed on the wire in order to have that current flowing. So you will see me in more complicated examples, you will see me using the gradient of the surface charge distribution to show how that gradient can result in the current.